Great. So first, let me introduce Peguy Pierre-Louis. He's the Solutions Architect Team Lead within Professional Services at D-Wave. Pierre has a PhD in Systems and Industrial Engineering with a focus on stochastic optimization. He has over a decade of experience building business applications and solutions in various industries, including finance, energy, and transportation. Let me also introduce at this time our guest speaker from Satispay. Calogero Zarbo is a lead data scientist with over 14 years of experience applying machine learning and deep learning techniques to various domains, such as personalized medicine, e-learning, and fintech. He has worked with optimization problems using D-Wave architecture for the last 5 years, supporting strategic decision-making. Currently at Satispay, as I said, an emerging Italian fintech focused on payments. He is mainly focusing his effort on marketing strategy optimization. So with that, we will start with Pierre. Thank you.
Thanks, Susan, and welcome everyone. It's a pleasure for me today to talk to you a little bit about the future of finance and how quantum computing is changing the game. Okay, so before we go into that, I wanted to also share with you a little bit about D-Wave. I know some of you are quite familiar with us, but some of you might be new. So I'll just really give you an idea of about D-Wave. So D-Wave has an established product portfolio. We have the world's most powerful quantum computer. Our advantage quantum annealing computer is in its 5th generation. It's a 5th generation system right now with over 5,000 qubits. So that is, in fact, the most powerful quantum computer. No other quantum computer has that many qubits, regardless of the modality. It's accessible through production-grade cloud service. Our Leap cloud service is a real-time quantum cloud and quantum hybrid solvers service, which has an uptime that's which has an uptime of 99%, over 99% uptime. And we also have open source Python tools, Ocean, that is easily configurable and that simplifies the use of quantum computing and our hybrid solvers. And at the end, I will talk to you a little bit about our launch program. So if you were new to quantum computing, whether you were new or whether you've already familiar, you've already embarked on your quantum journey, we have a program at D-Wave with the professional services, which is a customer on-ramp program that professional services work with customers to do application evaluation, from application evaluation all the way down to production deployment. We also have growing commercial adoption of our quantum annealing computers. This was the first commercial quantum computing company to attest to that. We have over 20 proven business use cases. And here we've listed some names of the customers that have worked with us, that have developed applications. Some of the names here might be familiar to you. We have Johnson & Johnson, BBVA, Bank of Canada, Lockheed Martin, Cassia Bank, Save On Foods. And as you can see, those names, those brands, those enterprises, they span a variety of industries. So we have a really strong track record of working with businesses in developing initial applications that can move into production for various industries. We also have a high-value consultative services, and this is something that's spearheaded by our professional services team. Over 20 successful proof-of-concept engagements in a period of 18 months, and that also come included with the advisory services to aid in production deployment. And more about D-Wave, very strong thought leadership, over 200 US granted patents, over 140 pending worldwide right now, 60% plus annealing and gate, and top 3 quantum patent portfolio globally. So this is a little bit about D-Wave, and now we'll talk a little bit about quantum computing. So what is quantum computing? And obviously we're not going to get into the physics and the detailed physics of quantum computing here. I mean, there are folks who can speak to that much better than I can. But at a very high level, the idea behind quantum computing is based on harnessing quantum mechanics for computational utility. And really, if you think about quantum qubits, the key thing maybe you might have heard about when making the distinction between classical computing and quantum computing is the fact that quantum bits can be in that superposition of states of both 0 and 1, versus for classical bits, you're either in one state or the other. That fact, among others related to quantum mechanics, really allow us to have great computational advantage when using quantum computing. But giving quantum computing a new computing paradigm, how do we determine the value of quantum? And there are two main ways we can evaluate the value of quantum. The first one, and that's typically the one that most folks think about, is, are we able to solve problems that had been unsolvable before, the problems that classical computers have not been successful in solving? And if we're able to do that, you can imagine the amount of social and economic impact. However, there's an equally important aspect to evaluate quantum computing, and that is the one that has to do with being able to solve current problems faster and or better. So it's not just enough, it's not just necessary to solve problems that we can solve, but even for those problems that we're able to tackle today with classical computing, quantum computing can enable us to solve them either faster, or if not faster, it enables us to find better solutions to those problems. And the implications here are somewhat obvious, right? On the one hand, that would lead to reduced costs, and on the other hand, increased revenue, if from the point of view of a business, and in particular from the point of view of businesses in the financial services. There are many different ways that the quantum computer can be built and have been built. But among all those different ways, when we're talking about quantum hardware, there are two primary modalities. And those two primary modalities are quantum annealing on the one hand, and gate model quantum computing on the other hand. Quantum annealing is very well suited for solving optimization problems, in particular combinatorial optimization problems. It's also easier to scale than gate. So typically how quantum annealing works is that you provide the solution space to the quantum processor, and as part of the anneal process, the annealer searches the solution space to find either an optimal solutions or a low energy state. And each one of these modalities has types of applications or problems that they're better suited for. And as I mentioned earlier, annealing is better suited for optimization, so combinatorial optimization problems, and examples of problems you can find under that category include, not limited to inquiry scheduling problem, for detection, patient trial optimization, autonomous vehicle routing problems, whereas on the gate model side, which really involve higher investment costs in learning curve, but the types of problems that theoretically gate model systems could be well suited for are differential equations, a problem where you have to solve differential equations, such as design of drugs, new materials. And then in between, there's an overlap. There are linear algebra factorization type problems where either gate or annealing quantum computing could fare relatively well. But currently, we have quantum annealing quantum computers that are ready to go, that are actually in use, and can solve enterprise problems at scale today. And that's not the case yet with gate. So what is the implication, or at least what is the state for the financial industry when it comes to quantum computing? So here we're going to look at the spending in the financial sector for quantum computing. In this chart here on the left, this is a chart that's from Deloitte, and it is showing both what's called offensive spending and defensive spending. And the terminology here is that defensive spending is in spending that has to do with infrastructure to counter vulnerabilities, security vulnerabilities, or general cybersecurity that might be exposed due to advances that are going to be shown with quantum computers, whereas offensive spending has to do with development, active involvement, active spending in building up quantum, building up talent for quantum computing, or in acquiring quantum hardware. And as you can see here, there's going over the next 10 years, and that's going back to 2022. We're already in 2023, at the end of 2023 here. Going all the way to 2032, there is both a significant rise and a rapid rise in spending, because at the end of what's projected for 2026 overall is about $600 million. But forecasting 6 years forward into 2032, we're already looking at $18 billion. So globally, the financial industry is increasing their spending capabilities for quantum computing. And there's an expectation of a growth of about 233x, as we've seen here. So it was 80 million in 2022 and 90 billion for 2032. Likewise, some research done by Hyperion also shows that optimization-based financial workflows will be the most significantly improved with quantum computing resources. And about 51% of respondents surveyed wanted to solve financial optimization problems. So that is the future for financial services, really, is quantum computing is going to have a very major role to play there, as these numbers and as this chart show us here. So here I wanted to spend a little bit of time and talk about some of the major some of the key category of applications in the financial industry. And obviously this is not an exhaustive list. This is just an example of where a lot of the applications are in the financial industry, what categories they will fall under. And later on, I will speak more to more specific examples in applications that are relevant to the financial sector. So banking and capital markets, risk management. So quantitative risk assessment models can be very complex and computationally expensive model. Quantum computing presents an opportunity here to analyze risk scenarios with greater accuracy. Fraud detection is another applications, financial services applications, where the use of quantum technology can enhance pattern recognition and enable financial institutions to detect emerging financial crimes swiftly and with more confidence. Complementing AI and ML workflows. So this is another area where, with the optimization offering that quantum computing has, especially quantum annealing, you can really enhance existing workflow, AI and ML workflow. We currently have a feature selection offering, and that feature selection offering can seamlessly integrate existing AI and ML workflow. Asset management, another major category of applications for the financial sector, in particular portfolio optimizations. So quantum computing can help to efficiently determine the optimal asset mix to maximize returns while minimizing risk in portfolio management. And well, I'll talk later on about a specific example of a customer who will have made use of our quantum computing technology to solve a portfolio optimization, to develop a portfolio optimization solution. Insurance and reinsurance, another major category of applications as well. Product pricing and insurance underwriting. The insurance industry is grappling with having to accurately assess risk exposure and converting it into insurance premiums, premium investments, and reinsurance. There's a lot of opportunity here in the insurance industry with using quantum computing to develop strong and resilient solutions. So what difference does quantum make? What are the quantum differentiators? Why the financial services need quantum computing? So here I'm really going to summarize a number of key points. And again, not an exhaustive list. There's a lot more that can be said here, but I think these 4 points here really encapsulate most of that. So number one, accurate modeling of complex problems. We all know that in the financial industry, I mean, there are a lot of very complex problems to be modeled. So annealing is a powerful resource for solving problems that arise from increasingly complex real-world models. And there's, as we've seen, there's a lot of opportunity here to get an advantage over existing classical methodologies. Enhance of solver capabilities. D-Wave's hybrid solvers natively support quadratic models. And the point here is that sometimes we see that models get simplified partly because maybe the solver that you're using is a linear solver and cannot handle quadratic expression natively. For instance, when dealing with portfolio optimization models, when you're modeling risk, a lot of times there are quadratic terms. Well, the D-Wave hybrid solvers are natively quadratic, so having to model quadratic expressions is actually very well suited, it's very natural, so you don't have to approximate that, so you don't lose on accuracy in the modeling. Accelerate time to solution in finance. Financial services enterprises can see real business value today as the technology accelerates time to solutions for many complex business processes. And as we're able to solve more complex problems, then you don't need to spend as much time either in simplifying the problem or maybe in having to solve more complex problems with the classical resources that are not well suitable for the complexity that are in the problem. Future-proofing financial services to maintain resiliency and a competitive edge. We've seen from the chart that I showed earlier from Deloitte Insights and the survey from my opinion research, we know that quantum computing is going to play, the financial industry is already responding to the role that quantum computing is going to play into the financial industry going into the future. So financial institutions are, and that's for two reasons. One, the defensive one has to do with making sure that they can respond to security threats and constantly changing financial market stability. And two, it's due to the increasing complexity in the problems that they have to solve, due in parts to shift in customer preferences driven by technological investments. So now I would like to share with you a few success stories of customers who have developed solutions using the quantum technology at D-Wave, and those are solutions that are applications within the financial sector. So first, CaixaBank. So CaixaBank built quantum solutions for investment portfolio optimization. In particular, they wanted to increase or maximize one portfolio internal rate of return while they minimize the capital needed for hedging operations. To do that, CaixaBank developed solutions using D-Wave quantum hybrid solver technology to implement a faster algorithm. So key highlight of some of the results that they obtained, they got up to 90% decrease in compute time with the quantum solutions over the traditional solutions. And while that in itself is a great result, there are further implications to being able to obtain, to reduce the quantum time, so the compute time significantly. It is the ability to increase the model complexity to better represent realistic market conditions. Because now that it takes a lot less time to solve the problem, now they can actually incorporate into the model more complexities that capture the real conditions and real scenarios for the problem that they want to solve. The next one that I want to highlight is from MasterCard. Improve fraud detection to save significant funds. So current approaches to fraud detection, they are limited by the number of features that they can use, and that in turn leads to lower accuracy that they could otherwise obtain, at least in theory. So MasterCard currently is working is using D-Wave's quantum technology to explore feature selections. I think earlier I've mentioned our feature selections offering. Our feature selection offering would allow them to be able to come up with a reduce an optimal set of features that will deliver the best possible machine learning model. So by reducing the set of features and by coming up with an optimal set of features, they're still able to train the model faster while they don't see any drop in accuracy. And in fact, while also possibly increasing the accuracy level. So there's a lot of business value here because indeed the limitation that they were seeing with not being able to incorporate all the features, our solutions with the D-Wave quantum technology allows them to be able to pick only the features that are truly relevant for the training of the machine learning model. And the next success story that I want to share with you here is from Good Lab Studio. They have improved the efficiency of their payment systems. And payment systems typically have real-time costs, they have high liquidity costs that are associated with the real-time settlements. And the Good Lab Studios, they have worked with D-Wave, they have used D-Wave CQM hybrid solver to develop the solutions that not only allows them to minimize the liquidity costs, but also it allows them to evenly distribute that cost among all the different parties involved in the payment system and the transactions. And some of the key results here is that they were able to process about 140 payment requests in under 16 seconds. And that resulted in a saving of close to $400 million in liquidity costs. So these are really great results. These are great success stories. And these are financial institutions that have used our technology, our D-Wave's quantum and hybrid solver technology to develop applications that bring them results right now. So if you wanted to start, so where do you start with your quantum journey? If you're new to quantum, how do you get started? If you're not new, how do you accelerate your journey right now? So I want to talk to you a little bit about our launch program, the D-Wave launch program. This is a program that's there for you wherever you are in your quantum journey, whether you are starting now, whether you're entirely new to quantum, or whether you're quite familiar where you have already embarked on the quantum journey and you want to make the next jump, you want to go to the next level. At the very beginning, we talk about what's called a phase 1 discovery. And that would be if you're entirely new, you're just getting started on your quantum journey. In that phase 1 discovery, this is where we would do use case review. And this is a program that is spearheaded by our professional services. It's a professional services demonstration bundle. So this is the stage, at that stage of the use case review, you do problem definition, and you can build a demonstrator. And the idea behind the demonstrator is to be able to demonstrate, at least for a suitable use case and a suitable example, that there is a possibility, there's a path to success for using quantum technology to build a particular application that corresponds to that use case. And this is typically a 1 to 2 month engagement that can lead to a likely demonstrator, as I mentioned. In the next phase of that, again, you don't have to start at phase 1. Maybe if you have already defined your problem, maybe there are customers who've already defined their use case, the problem is already defined, and they can start with the phase 2 directly. So phase 2 is a quantum proof of concept. And for the proof of concept stage, this is where we would work with our professional services and to develop solution requirements, work on developing a prototype, and do testing and evaluation. And this is a professional services proof of concept bundle, and typically a 3 to 5 month engagement to build a proof of concept. And again, it's a range partly because this is going to be adjusted based on where you are, based on the nature, on the problem, and based on what's needed. So it's not a one-shoe-fit-all scenario. Beyond phase 2, we have phase 3, which is production pilot. So if you now having defined a problem, having developed a successful proof of concept, you can work on a pilot application. During that phase, so what we would do, we would work on developing a pilot, do pilot testing, and come up with a plan for deployment. That phase is a QCAS development bundle. QCAS, that's quantum computing as a service. And that comes with advisory services. So we would provide advisory services to you as you work with pilot applications after it has been developed with our support. And this stage of work, this phase of work, production pilot, it is a tailored engagement to develop the pilot applications. And ultimately, phase 4, that's in production. So full-scale deployment, integration support, including our Leap Quantum Cloud Service Access, is the QCAS production bundle. Leap Service Access is included, as well as advisory services to support the application in production. So at this point, I know that I have shared with you 3 success stories, but I know what I actually shared with you were highlights of those success stories. But what we would like to do, we want you to hear straight from the source. That's why we have invited one of our customers, Cal from Satispay, who's going to walk you through one of his success story with working with our D-Wave quantum technology. Cal?
Hi, everyone. Well, thank you. Thank you. It's a pleasure to be here, actually, talking about what we managed to do thanks to the support of D-Wave. And yes, next slide, please. So what I'm talking to you is how we grow our customer base. So as a payment network, our success is measured in how many people is using our payment method. So at the moment, we deliver the payment method as a form of an app, but regardless of the form on how you pay, is the infrastructure that we use and that we build, and the people, the community that we build, that matters at the end. So one of the simplest but most effective way to increase your customer base is using the reward program. We call them member get member. And this type of approach has been proven very successful during the last years, leading us to become a unicorn last year and account for the vast majority of the new customer that we managed to onboard. But at the same time, is a huge figure in our business statement. So we're talking about around 25 million per year of marketing budget, and a huge portion of it is used in the reward program. So any little optimization in this regard usually bring a lot of free resources to use in other dimensions. Pierre, next slide, please. So in order to optimize the reward program, we first need to understand our customer. Who is our customer? So basically, we want to understand the patterns of the behavior of the people that use the app, of the people that use the payment method, and to do so, we wanted to understand this using machine learning. So basically, we devised a series of models. These models targeted the features describing the payment behavior of our customers, and understand which type of reward they might most be suitable for them. So most of the time, you do not have enough data from the past in order to understand what they behaved. Sometimes you have new customer in, and willing to fill all this historical gap with the true measures is really costly. It needs that you need to do randomized experiments every now and then. And every time you onboard new customer, you still have gaps to fill. While using machine learning, you can then understand which pattern actually drive the behavior and the use of the reward program. But once you understand this, and when the machine learning tells you the best patterns that lead to a particular reward to be used, then you need to make a decision because you have a limited budget. So under this budget constraint, you need to assign some reward to some customers, some other reward to some other customers. So at the end of the day, you don't want to spend too much, but you don't want to spend too few. Otherwise, your customer will not use the reward. Next slide, please. So just briefly, in order to do this predictive profiling, we used a library called Wide and Deep that was devised by Google, and we used a particular transformer model, which is called feature transformer. We decided transformer models over other type of modeling because the patterns that discriminate between someone who could use the reward and someone that do not use the reward is very, very difficult to spot, and usually the other simpler models tends to classify them as a noise instead of a real information. Next slide. So the output of the machine learning is this curve. So we can see on the x-axis the type of rewards, the amount of the rewards, and on the y-axis what we call the appreciation level. So here we can see that every line represents a different customer. Here I draw 20 different customers, and we can see that we have different behaviors, meaning that sometimes people do not even like 50 euros, for example. Others do not use nothing except 50 euros. For others, 30 euros and 40 euros are the same. So you have these different, let's say, feelings, perceptions of the rewards, and you need to take decisions having budget constraints. Next slide, please. So in order to make this decision, then we needed to understand how to formalize the optimization problem. And this is where we understood that we need a fast solver to tackle our problem. So we modelized the problem using P as the output of the machine learning. So no information about my customer is sent to D-Wave whatsoever. Everything stays internally. So any problem regarding data privacy is basically solved at that point, because we just use the output of the prediction in a particular vector. So I know that customer 0 have probability 0 and customer 1 has probability 1, and I know on my end which one is the customer 0 and customer 1. So I feed the probability, and then X is basically the qubit. So either I will activate or not activate that particular reward for that particular customer. And C is the cost of the incentive. So either I'm going to give 10 euros, 20 euros, 30 euros, 40 euros, whatever. So I would like to maximize the appreciation level of the campaign, which then will result in many people using the rewards, and therefore many friends to be invited into the payment network. And I would like to respect such constraint. For example, only one reward can be submitted to a particular user. So I can't give multiple rewards at the same time to the same user. And I would like to have a CAC, which is customer acquisition cost, which is not more as an average of the whole campaign of a certain target. So let's say that I have a particular target cost, which is around 30 euros. Well, then the average cost of acquisition should not be above that 30 euros. So I will have some customer acquired at 10 euros, and I have some customer acquired at 50 euros. I just need to find a way to balance those out. Otherwise, I will overshoot to the cost of a campaign, which is exactly what I do not want. Sometimes the marketing team provides me also the some bare minimum level of appreciation target. So, I mean, the campaign can be executed only if you respect the customer acquisition cost target, but also if you reach at least a minimum appreciation target. So I have the upper boundary and the lower boundary, and then I need to find the optimal or suboptimal solution in the middle. Next slide, please. So the whole system basically looks like this. We have a huge relationship with our BI team, and I work in the advanced analytic team, so they call AI team. So the BI and the AI team work together because data is 80% of the value of everything you do when you do advanced analytics. Then there is a deep learning system that is basically doing deep learning for causal inference. That's if we want to be scientific on that, that's what you should call it. So we try to estimate a probability of activation, so of a probability, I would say a level of appreciation of your customer that is described by X covariates under the treatment T, which the NT is the reward that you give to him. And then we submit the decision problem to the D-Wave system. So all that math that you saw in the previous slide is basically translated into a Python program. And then I used the CQM, so the constrained quadratic model, that is really suitable for this type of task. And when I transform it into the Python program with all the constraint for all my customer, I then submit it to D-Wave, and then I get out the results, which is basically the allocation. So which customer is served with which reward, and then I submit this allocation to marketing that then trigger the campaign. Next slide. So in order to understand if this technique was better than before, we needed to A/B test it, use it, and then you need to have like a metric of success. So previously, the marketing team has a different approach to this problem, and now we would like to give them a tool that is actually performing better than the previous one. So our KPI was to at least generate an uplift between 5 and 10%, then in order to justify all the effort. So in order to evaluate this effort, we arrived to this kind of matrix. So in the center, the point A is the control group, which is the standard marketing practice, and it's basically normalized 1 and 1. So you have it every time in the middle. And if we move on the right, we are going to spend more than marketing. And if we move on the left, we are going to spend less than marketing. If we move up on the y-axis, we're going to acquire more customer than what has been done by marketing. And if we move down, we're going to acquire less. Of course, if we spend more and acquire more, we are not really doing any optimization, because I mean we are just moving on the same, let's say, on the same wave of efficiency. Next slide. The problem starts if I spend more and acquire less. It means that I'm totally inefficient and my presence in the project is not justifiable. Next slide. If I spend less and acquire less, well, that's not exactly what I'm hired for. So I mean, it's like if you don't buy anything to the Black Friday, you're saving 100%. Yes, of course. Next slide. What we want to do is that if we want to spend less but bring more, that's the real quadrant of efficiency that we would like to achieve. Next slide. So we ran the first A/B test. So we wanted to see if we can pump the return. And so we settled the objective function to bring as much as we can possibly get with a particular target. In this time was around 30 euros. So we managed to spend like 30.50 cents like 30.50 cents, but we brought like 80% more than what marketing actually did on the same population at the same time. Next slide. Then we wanted to see if we could bring these results in the area of efficiency. We understood that yes, we can spend less and bring a little bit more, but the results drop dramatically, at least in the district that we tried this A/B test. And this is a clear evidence that the problem is highly nonlinear and most likely an exponential function, meaning that if you spend a little bit more, then you can get a lot more. But if you spend a little bit less, then of course you drop by a lot of returns. But still, also in this test, we are above the KPIs because this is a plus 25% in return and less 10% in costs. So we passed both A/B tests, and we decided to go live, I would say 100% with using this tool in order to save time to marketing that do not have to do this campaign manually, but they use this tool to create the allocations, and it runs every week. So every week we have like 1 million customer that then enters into this system, and then we allocate within a couple of hours. Next slide, please. What actually mattered for us, which is why we decided to use D-Wave, it wasn't the quality of the solution itself. It was the time to the solution, because by the formulation that you saw, it's pretty linear for the time being. So we don't really need a quadratic solver, but a linear solver like Higgs or Gurobi or you name it take ages to solve the size of the problem that we need to solve. So when we run one campaign, so 1 week, we have 1 million users, and we have to choose between 4 different rewards, which makes 4 million variables. So someone can say, how can you do this if the hybrid solver has a limit at 500,000 variables and 100,000 constraints? Well, I simply slice the problem into chunks according exploiting geographical information, meaning that I put close together districts, provinces that are close together geographically speaking, and so I submit one problem at a time that max out the 500,000 variables and the 100,000 constraints. And then I take back the solutions of the different sub-problems, I merge them together, and I have my final allocation. This process takes 3 hours. If I was doing this into a classical environment, I could get up to 3 hours, but the number of machines that I have to spin up on Amazon and the time that it would take to me and to the DevOps team to take care of the cluster and the maintenance and so on, it was actually inefficient at the end of the day. Here I just have my token. I bring I just have my Python script with the token. I send the problems, and then I gather the results, and then I can give the allocation to the marketing team. So the next, so here I'm mentioning that the number of simulation that I need is 3, because let's assume that I want to maximize my return at 30 euros, then I see what I could get at 28, what I could get at 32, and then ask to the marketing officer, but do you really want to spend 2 euros more per customer, knowing that you might get like other X% more than before? And then the marketing officer can say, can usually tell me yes, because these districts are very important to me for our business plan, or no, because these districts at the moment are not the focus of our strategy. So these 3 simulations help us understand if we want to spend a little bit more or a little bit less. So, and we can do it because we save a lot of time on solving the problems, and therefore we can evaluate more scenarios. When these results was seen by my CTO, Dario Brignone, actually he something triggers in his mind and says, well, with this kind of speed, why we don't go real time? Meaning that as soon as a batch of new customer arrive, then you can optimize a new reward program specifically for them. So, and this can be done thanks to the a particular setup that D-Wave can do for us that basically increase the parallelization of our jobs by 3 times. So we could actually do the same job that we do at the moment with 30 minutes, 40 minutes, depending on the size of the problem itself. I think I said it all, Pierre.
Wonderful. Thank you, Cal. Thank you, Pierre. Pierre, if you just move to the next slide. We had a number of questions come in, and some of them were about, well, how do I get started if I'm new to quantum? So we have a lot of resources and ways to get started if you're a developer or if you're a business trying to understand how quantum might benefit you. So here are some links. Again, we will send out these slides and a link to the recording over the next week. The best way to get started from a development standpoint is to sign up for a free Leap account. So Leap is our quantum cloud service. You can go sign up for a free account and get real-time access to the system. And there are lots and lots of examples and code on GitHub that you can look at. There's just a ton of resources within Leap to really kind of start you on your quantum development journey. We also offer training classes. They're week-long virtual classes with live instructors, which are really the best way to kind of jumpstart learning about quantum. So again, those are some ways to get started. So we have time for a few questions, but before we do, I'm going to launch a poll, if you wouldn't mind answering a few questions, and you can see them all here. So we're interested to find out whether you've actually started working on a quantum application, what financial use cases might be of most importance to you. And then the third one is, what was your reason for attending this webinar? So we'll give you a minute or two to answer, and then I'll go through and ask our presenters some of the questions that have come in. All right, we'll give you a few more seconds for those who haven't finished it yet. All right, so I will leave it up while presenters, or they both come back on camera. We can go through a few of the questions that came in during the talk. First one is for Pierre. Would you just kind of briefly explain the difference hardware-wise between annealing and gate model systems?
Pierre, quick question.
We don't see you yet. Oh, there we go. Okay.
Oh, you don't see me? Right. Yeah, so quick difference here. So annealing and gate models are just 2 modalities. It's just 2 paradigms. It's 2 modalities of quantum computing. So the hardware is a separate story. So for instance, at D-Wave, so we've already built annealing quantum computers, but we also have a gate model program, and they're both, the hardware that we use is a superconductors. So it's a similar hardware that we use. So the hardware can be different, it can be the same. So it's just that in one case, annealing is designed specifically where you actually provide the solution space to it, and it's good to solve optimization problems. Whereas for gate model, it's more general. So you have a gate system where you can specify a sequence of arbitrary operations. This is something more similar to what we're accustomed to classical computing, where you can provide a sequence of operations that the computer needs to perform.
Okay. Can you give some specific application of quantum computing in insurance or reinsurance?
I think one thing that I had mentioned was premium, setting premiums, so premium optimization, so in the insurance industry. So I think that's one thing that I had mentioned. I mean, there are other cases that you could, so oftentimes one way to come up with a particular application is to think about what aspect of a particular process requires optimizations, and sometimes it's not always evident. But price optimization, premium optimization, segmentation of customer, these can be type of applications that may apply to the insurance industry.
Okay, great. Let's see, I'm just going to go down here. And look through it. How do the pre-solve techniques best enhance fintech applied through the D-Wave solvers? And actually, Pierre, maybe you just want to briefly explain kind of a hybrid solvers for those that don't know what they are.
Right. So our hybrid solver, so we have the CQM, which is a constraint quadratic model solver. So essentially, hybrid solvers make the best of classical and quantum resources. So where you can express a problem in a mathematical natural way, where you have an objective and you have constraints. So that way you don't have to think about, so if you wanted to solve a problem directly on the QPU, you would have to think about the topology of the QPU, and you would want to encode your problem in a way that would fit the topology of the QPU. Whereas with the hybrid solvers, that's not the case. You can think about the problem in a mathematical way, and behind the scene, we take care of that. I mean, we have proprietary software that actually can take your problem and determine what parts of it is best suited for quantum and what parts of it are best suited for classical. So now that's on the hybrid side. And what was the question, Susan, if you don't mind repeating again?
Well, why don't we just kind of move on, because we have a few other things. Okay. A question for Cal, and actually, Pierre, you can kind of jump in terms of how this is priced. How much was the cost of this 3 hours of simulation? And clearly that 3 hours was not all 3 hours of quantum processing time. And the second part of the question, Cal, is it possible to run the simulation on a gate system?
Well, the second part of the question, actually possibly to run on a gate system, I don't think so, because the number of qubits needed to encode the problem is simply unfeasible for the gate system that at the moment we have available. And about the cost, well, I need to make some math, but I mean, I did this some time ago, but I wouldn't say more than $200 to $300 per campaign. Because I mean, if I have to, roughly speaking, 1 hour of quantum computing, according what kind of contract you get and what kind of launch program you have, might cost $125 per hour. But that really depends on. So if we take that as an estimation, and I take 3 hours, then it's not more than $400 per campaign.
Okay, last question, and then I'm going to show the results of the poll. We will try and get back to everyone who has asked questions over email. We don't have time to go through them all. How do D-Wave solvers compare to classical solvers in terms of duration, problem size, and costs? Do you have some benchmarks that we can show potential clients?
Yeah, so we do have a lot of really interesting benchmarking results, and I don't I don't have specific numbers I can cite to you now, but I can point you to again, like Susan said, we can follow up with some with more resources. But we have one very important result that was published that showed advantage over classical was published. It's a paper that was published in Nature. So we have a lot of very key results like that have been published, and we can certainly follow up with specific links to those results.
Great. Thank you. And again, there's a ton of resources on our website, both in terms of publications. We have lots of kind of case stories. We have a number of them that kind of talk about projects that have been done versus classical solvers like Arobi, et cetera. So let me just briefly share the results of our poll here. So let's see. In terms of people who've already started working on a quantum application, for those people that answered it, 39% said yes, which is a nice high number. In terms of the use cases, 57% for portfolio optimization. You can see the rest, 42% risk management, fraud detection, offer allocation, and the ever popular other was at 36%. So with that, I'd like to very much thank everyone for attending. I'd really like to thank our presenters, especially our guest, Cal from Satispay. It was very interesting. Again, you'll get an email from us in terms of links and links to the slides and the recording. And our next webinar, you will get some information about as well. It'll be a very interesting use case from Savantex, and that will take place January 11th. So again, thank you all for coming. Thanks so much, Cal, and thank you, Pierre. Hope everyone has a great day.
Thank you. Bye.
Thank you.